Hello, welcome to today's lecture number 4 for Introduction to Astronomy, AST 1002. Today's lecture is on radiation, spectroscopy, and the various telescopes that we use in astronomy. In this lecture, we will learn about the visible and invisible universe. We will learn about the electromagnetic spectrum, which is light. We will also learn about spectroscopy, which tells us a lot about colors and temperatures and compositions of objects very far away, as well as close up. And we also will talk about telescopes and how they are very, very varied in their design and their uses and the wavelengths that they look at. And we will also learn about the different wavelengths that astronomy looks at when it is being done. So we're going to talk about the observable universe. That is all of the universe that we can see with information from the electromagnetic spectrum or from gravitational waves. And then we can think about the observable universe as being divided into two groups: that which we can see and that which we can't see but we can still observe, such as things outside of the optical part of the electromagnetic spectrum. So it's really easy to think that that astronomy only focuses on the visible universe and what we can observe optically. But after the discovery of Uranus and Neptune, astronomers were able to see that by using mathematics and very advanced astronomical theory, they could postulate more about the universe than we could see with our eyes. So all light is a form of radiation. It is energy that is radiating around. It's radiating towards us. And so when we see light from distant objects, we are seeing visible light radiation from those objects. Visible light is what we see with our eyes and is what we think of mainly when we think of the visible universe. But that's not the only form of light radiation that we use in astronomy. We've talked about radio waves and microwaves, and we'll see infrared. And honestly, every part of the electromagnetic spectrum has an application in astronomy. So light can take on a lot of different energies and have a lot of different wavelengths. And so this wide-ranging term for all of the different wavelengths that it can take on, we call this the electromagnetic spectrum. These are all of the different wavelengths or energy levels that light can have. And so the discovery and formalism of this spectrum was made in the 19th century by James Maxwell and Michael Faraday. Maxwell did so much work with electromagnetism that the main equations used in high-level electromagnetism are called the Maxwell equations. So using their studies, our understanding of the universe shifted from a series of elegant equations into this electromagnetic spectrum that we call light. Suddenly, what we thought was a lot of different phenomenons were actually one, unified under this theory of electromagnetic radiation. So now we'll look at Rutherford's atom. This is one of the more simple models of the atom. And while it was simple and is not necessarily fully accurate and applicable to all of today's theories, it actually was still very useful for Maxwell in developing his theories of electromagnetic radiation. And that's because a lot of the aspects of Rutherford's atoms are correct. So Rutherford stated that atoms were very small particles, and those particles were composed of nucleons and electrons. And every one of these particles has two physical properties: mass and charge. So the nucleons are the protons and the neutrons. They are the particles that reside in the nucleus. Protons are positively charged, as their name sounds, and neutrons, as their name sounds, are neutrally charged, meaning they have no charge. They have a zero charge. They're neutral, the neutrons. And it was Rutherford who discovered that the nucleus was very massive and positively charged. The atomic nucleus is also very heavy. and it is orbited by electrons. But it is not orbited by electrons by gravity, but rather by electromagnetic radiation and the forces and attraction between the charges. So electrons are much lighter, they're negatively charged, and they carry a lot of the energy of the atom. And so in this course, we'll focus on the two simplest elements, two simplest atoms in the universe, and they're also the two most abundant. So they're the two most important for astronomy, and that is hydrogen and helium. Hydrogen is composed of one proton in its nucleus with one electron around it, and helium is composed of two protons and two neutrons in its nucleus with two electrons orbiting around it. We'll also see later in this course that there are isotopes, that is, there are versions of these elements that have slightly different particles in them. So, like for instance, there's versions of hydrogen that have a single neutron in the nucleus. They're unstable, but they do exist, and so we'll learn about those later in the course as well. Maxwell's theory of electromagnetism describes how charged particles behave and interact with the fields of magnetic fields and electric fields. We call this combination electromagnetism. In the 19th century, the existence of both electricity and magnetism was already known, but the way that they were connected wasn't. And it wasn't until Maxwell's theory was presented that a framework was established that connects magnetism and electricity. So now we know from Maxwell's theory and the extensive testing behind it that magnetism is the result of a moving electric field, and electricity is the result of a moving magnetic field. Put another way, changing electromagnetic fields induce one another. They cause each other to happen. This phenomenon is known as electromagnetic induction. The combined wave that results from an electric and a magnetic field inducing each other is what we call an electromagnetic wave. Electromagnetic waves are everywhere in our universe. There are radio waves passing through you right now from talk radio stations, from your Bluetooth, in your phone, in your computer. Hell, your phone is even connecting right now and sending and receiving electromagnetic waves. These electromagnetic waves share a lot of the properties of waves you already know about, like ocean waves and sound waves, or like kinematic waves in a rope that you're moving up and down. But electromagnetic waves are also very different. So they travel at extremely rapid speeds, the speed of light, and they also don't need a medium to travel through. So ocean waves travel through water, sound waves travel through air. Those kinematic waves that I just mentioned travel through that rope that you're oscillating. However, electromagnetic waves don't need a medium to travel through. They can travel through the vacuum. Just like the vacuum of space has light traveling through it. It was originally thought, though, and hypothesized that there may be some sort of medium, some sort of invisible material that light is traveling through that fills space. And this was called the aether, but no evidence has been found for it. In fact, a very famous experiment called the Michelson and Morley experiment seemingly disproves the existence of this aether, what they call the luminiferous aether, the medium that they thought light needed to travel through. But we now know that light can travel through anything, a vacuum even. And so Maxwell suggested that all the light that we observe around us is just one form of electromagnetic waves radiating from oscillating charges. And the equations that he derived were consistent with this hypothesis. All waves, including electromagnetic waves, have physical characteristics that determine how they behave. The most fundamental aspect of a wave is that it has a repeating pattern. Waves return to the same point through periods of oscillation. And this really makes sense visually when we see representations of waves on the right side. So some of these characteristics of waves that they all share is that they have a wavelength. That is the horizontal distance between or traveled by the wave between one period, like between the two crests or the two troughs, one complete cycle of the wave. That physical horizontal distance is the wavelength. Now, another proper characteristic of waves is their frequency. Frequency is the number of times the wave repeats and oscillates in a given amount of time. The unit that is used in the SI units for frequency is the hertz, which is a unit of 1 over time. So the inverse of time. So it's how many per second. So you can think of velocity as having a frequency as well, as being partly like a frequency, because velocity is the distance that a wave travels per second. So it's how many meters, in this case, per second is the velocity of the wave. So we can see that wavelength and frequency are related to velocity by this equation, v equals wavelength times frequency. And for electromagnetic waves in the vacuum, they have a constant velocity. They all move at this speed of light that we call c. It's not shown, it's not written here as c, it's written here as v, but the speed of light is incredibly fast. It's 3 times 10 to the 8 meters per second, or almost 300 million meters per second. Another property of waves is that they have energy, and this is what gives them their capacity for motion. And this is proportional to their frequency. This equation, given by Bohr and Einstein, of E equals hf, tells the energy of an electromagnetic wave given by a proportionality constant and its frequency. So what to take away from this is if you have a wave has more energy, it is a higher frequency wave. An electromagnetic wave, if it has more energy, it is a higher frequency. So if we've got a bunch of light sources out there, a bunch of stars and hot gas that's radiating, how is space not just entirely flooded with light? Well, this is because light's intensity drops off inversely proportional to the distance from the source squared. So this is called the inverse square law, and it means as we get further away from objects, the brightness we see gets smaller. Another way to think about this is that we could have a series of spheres around the light source that we're looking at, and then we could draw on those spheres a little square. And when we are 1 unit away, I'm sort of describing this drawing on the right, where we are 1 unit away, we only have 1 square. But as we move further away, the light is spreading out and having to go through this larger sphere. We have the same amount of light, but it now has to cover this in a much larger sphere. So the area that it goes through is now 4 of these squares because we are 2 units of distance away, and so on. So once you are 3 units of distance away, the light has to go through 9 of these little squares. So we can think of this as the amount of the light waves per unit area decreases as the light radiates further away from the source, because that same amount of light hasn't changed. It just has to cover a larger area as you're further away. So this is where things start to get complicated by what we call quantum mechanics. So this leads to a behavior known as wave particle duality. In the beginning of the 20th century, scientists began to observe that light often would behave as a particle even though it could be modeled and make you could make predictions with it being modeled as an electromagnetic wave. It still would behave often like a packet of energy, what we now call a photon. And as experiments continued and progressed, it became really clear that light would behave as both a particle and a wave, giving what we call this wave particle duality. This really contradicts our classical understanding of nature, which posed the question, how could something behave like a light or both like a particle and a wave? And this was the foundation of quantum mechanics. When we think about light, which is traveling at the speed of light, which is the fastest velocity that you can go in the universe, and it doesn't even require a medium to go through, well, it kind of makes sense that light must behave like nothing else that we know of in the universe. By using these models of Maxwell's equations and our understanding of quantum mechanics, it has now become possible for scientists to record all types of electromagnetic radiation in the electromagnetic spectrum. We can create instruments that can record the smallest wavelengths. Also, this is the same as the highest frequency waves. These are gamma rays and gamma waves. We can we can record those instruments. We know that supernova release gamma rays because we are able to record in that part of the spectrum. On the other end of the spectrum, we have the radio waves, which have the lowest energy and longest wavelengths. But there are a lot of different telescope designs necessary to record in all of these different wavelengths. And we had to design them differently than we do optical telescopes because light out is different outside of the optical wavelength. It is focused differently and it has to be recorded differently when we are working outside the visible spectrum. And the visible spectrum occupies a very narrow region of the electromagnetic spectrum. The visible spectrum corresponds to only 400 to 700 nanometer wavelength light. So, one thing that's really useful about understanding electromagnetic radiation is that we can measure the temperature of distant objects. And this is because temperature is directly correlated to the particular types of radiation being emitted by celestial objects and by how much they are emitting of that radiation or that electromagnetic radiation. So we have to first imagine all celestial objects as being an ideal black body. They aren't they aren't perfect black bodies in nature, but we can consider them as being relatively close. So you might be wondering, what is a black body? Well, this is a term from thermal physics that deals with that describes an object which is capable of absorbing all incident radiation of all energy levels. And it also then is able to radiate out energy, uh, able to radiate out electromagnetic waves that balance out what it absorbed depending on the wavelength of what it absorbed and the wavelength of what it's emitting and the temperature of the black body. So we can really take away from this is that black bodies emit radiation at all wavelengths, which give them a broad spectrum of electromagnetic waves. As you get to higher temperatures, the radiation is more powerful at all wavelengths, and the higher the temperature, the shorter the wavelength which is being emitted at max power. So when we look over at this graph on the left, we can see a black body spectrum for an object, a black body, at different temperature levels. So the coolest one, which is indicated by the 2500 Kelvin and the orange line, we can see that that black body spectrum is much lower. It is pretty flat. It has a little bit of a bump a little bit after 1000 nanometers, but that's primarily going to be emitting in the infrared. But then as we get to 3400 Kelvin with the yellow line, we see that that peak is moving up, and like the peak, which corresponds to the maximum intensity being received for that wavelength. And as we get all the way up to the 5500 Kelvin line, we see that the peak is now well within the visible part of the spectrum. For something that is 5500 Kelvin, we see that it has a peak about in the yellow. And this is about the surface temperature of the sun, which we know is a yellow star. And on this graph, we can also see an equation called Wien's law, which gives the wavelength that is being emitted at the maximum power for the temperature of an object. So if you were to put in your temperature in Kelvin, you would get out a wavelength that peaks in the infrared. And this makes sense because we're not glowing in terms of bright visible light, but when you look at our bodies in an infrared camera, you can see us glowing with our heat. So this brings us to the idea of this correlation between temperature and color, color being the peak wavelength that you are emitting. So for a lot of the EM spectrum, measuring the wavelengths required new technology. But when we look at things in the visible spectrum, we can use color to what we call color within the visible part of the spectrum to indicate temperature pretty well. So if we have a red star, that means that its peak wavelength is in the red of the visible light. And red has a larger wavelength in the visible spectrum. Therefore, the frequency of that light is smaller, it's less frequent, and it has smaller amount of energy. So this must mean it's a cooler star. This must mean, in contrast, when we look at a blue star, this means that this star is emitting higher frequency light that is with a shorter wavelength than the red star, and that light is more energetic. So this means that a blue star is hotter than a red star. And this makes sense from if you've ever had like a campfire, you know that the embers are cooler than the flames, and the embers are kind of glowing red, but then the flames are much hotter and they're yellow. And if you ever had a gas stove, which is burning, even that gas is burning hotter than a campfire, those flames are blue. And this makes sense with our observations and now with our knowledge that we've gained from these lectures. We can now make sense of how temperature and color are related. This generalization, though, is true because we primarily see the highest flux, the most intense EM waves for a star. And we can simplify this in the Stefan-Boltzmann law, which states that the amount of flux, the amount of energy received per unit area, or the amount of energy, radiated energy received per unit area for a black body is proportional to the temperature to the fourth power, with some constant of proportionality in there as well. When we look at radiated light without filters, we are looking at a spectrum of different wavelengths. So we're receiving all of the wavelengths at once. Isaac Newton first observed this spectrum when he used a prism to pass white light from the sun, and he noticed that there were various colors coming through. White light is a continuous spectrum, meaning that white light is made up of all of the wavelengths in the visible part of the spectrum. And when that white light passes through a prism, they reflect and refract through the prism walls, and they emerge and this dispersed rainbow of their individual wavelengths. Using this principle, we can now actually distinguish what elements are present in distant objects, as well as also if you're studying something really up close, you can do that as well. We now can determine, based on the light that's being emitted by an object, what elements are present there. This is a study known as spectroscopy, where astronomers study the spectral lines of light that are interacting with the different elements that are present. And so every spectral line is unique because elements have different numbers of electrons and molecules have different configurations of their electrons. Every element and molecule has a unique spectra. And this is very useful for astronomers to determine the composition of distant objects. There are several different types of spectra. So for the first one, we have our continuum spectrum. We have a white light source, which is our continuum source. We pass that through a spectrometer, or also a prism. And when we look at the spectrum through the prism, we get a continuum. It's still just all of the possible waves spread out in our spectrum. Now we have our white light has been spread out into this continuum spectrum. But there are several other types of spectra. And so let's think about an individual element by itself. And if we got this element excited, it would produce its own radiation. So excitations in this case mean that we have the electrons that are orbiting in our atom. They can orbit at certain energy levels, which we'll see more later on. And as they move between these quantized energy levels, they can emit light that is particular to the energy that they have as they move between those levels. So this gives us an emission line spectrum because the energies are emitted at only specific levels. So rather than a continuous rainbow source, we have individual bright lines, emission lines. And this is contrasted by our other type of spectrum, an absorption line spectrum. So when elements interact with a continuous spectrum, such as having a white light source behind our element of interest when we are looking at them through a spectrometer, that element of interest will absorb some of those particular energy levels from our continuum source. So when we look at our spectrum through our spectrometer, we'll see that those energy levels, those lines that were absorbed, are no longer present in our spectra. We have these black lines, these gaps in our spectra, and these are absorption lines, which gives us an absorption spectra. So on the last slide, I mentioned about electrons and energy levels, and those of you who haven't been introduced to that concept before may have been wondering, so let's now really dive into that. So after Rutherford discovered the atomic nucleus, he hypothesized the orbital model of the electron. But it wasn't until Niels Bohr, or not Niels Bohr, Nicholas Bohr said, why do electrons stay in their orbits? And this helped explain one key piece of the puzzle. Bohr hypothesized that electrons had to be confined to specific energy levels called orbital shells around the nucleus. When an electron was in that orbital shell, no energy is lost or gained as it moves around in this shell. Only when an electron moves between shells or is what we call excited does it gain or lose energy. This was the process known as quantizing the energy levels for an electron. We gave specific values to the energy levels for an electron. We quantized it. Quantum mechanics, quantizing, giving these things specific numbers and values and particles is where we kind of got this idea of quantum mechanics, quantizing things. So when an electron loses or gains energy, it has to go somewhere. And if it is absorbing incoming energy, it can jump to a higher orbital shell. This is what gives us that absorption spectra. But electrons don't want to stay in their excited state. They will eventually emit that energy out and fall back to their ground state. And so they will emit a photon of a corresponding energy between their excited level and their ground state energy level. So this quantized diagram of electron shell energies is the foundation of quantum mechanics, which actually led to improvements in Maxwell's theory and helped bring a new theory called quantum electrodynamics. With 118 elements in our universe and countless more possible molecular configurations, this means spectroscopy can become very overwhelming for astronomers to understand. And we haven't even talked about ionization yet. So, ionization makes this even more complicated. Ionization occurs when incoming photons have so much energy that they can knock off one or more of an atom's electrons. And you can have ionization happen for as many electrons as that are present in an atom's orbital shell. So, for example, neutral helium has two protons, two neutrons, and two electrons. When it is singly ionized by an incoming photon, it removes one electron and becomes helium 2. And when it is doubly ionized, when both of its electrons are removed, it becomes known as helium 3. So we can now think of neutral helium as being helium 1, but no one refers to it as that. They just refer to the first singly ionized state as being helium 2. So since the spectra of an element is dependent on the number of electron excitations, and electrons ionization removes some of these electrons from spectral lines, this makes it very complicated because astronomers can spend like their entire career studying how various spectra are possible while trying to account for distinct missing bands that happen due to ionization events. So understanding spectra really requires a deep understanding of the physics involved in these elements at play. There's even more possible ways that element spectra can be affected, and one of these ways is the Doppler effect. So, electromagnetic waves are often coming from moving sources because nothing in our universe is actually standing still. Everything's moving relative to each other. So, their Doppler effect is very important to understand. So the shift in an electromagnetic wave's wavelength when it's emitted from its source due to its motion is what we call the Doppler effect. It's that shift in the wavelength. So in astronomy, there are two types of shifts that occur from the Doppler effect. This is redshift and blue shift. Redshift occurs when the source is moving away from the observer, which in effect elongates the electromagnetic wave, shifting it towards the red if it's from a visible source. Or if the object is moving towards you while it's emitting light, this is known as blue shift because it has the effect of shortening the electromagnetic wavelength from the emitted light. And what's important to remember is that redshift and blue shift just generally refer to a lengthening or a shortening, respectively, of these wavelengths. Sometimes it does actually change the color to become red or change the color to become blue, but we are just using these terms for their apparent shift in their spectra relative to their wavelength. So now that we understand how light behaves as both a particle and a wave, and how it travels through space in the vacuum at the speed of light, and we've seen how light is in a spectrum, and how that spectrum of emitted light can be affected by different emission or absorption processes, and we've also seen how those spectra can be affected by ionization and a Doppler effect. Well, now we need to know how we actually record things in astronomy. And so all astronomical instruments start out similarly and have three main components. So these components are the telescope, which is the device used to collect the incoming radiation while keeping it as intense as possible. This means that we want the light to be collected, but we also want to make sure that we're getting as much of it as possible. And then the next element is called the resolute. You can also think of this as a sorting device. And this improves the quality of the incoming wavelengths, and it helps focus these waves into an observable spectrum if these light waves are outside of the visible spectrum. And then finally, we have a detector at the end, which is a device that is used to detect and measure the radiation that is incident to it, so that it is what actually records the electromagnetic radiation that we are interested in. And it also records the intensity of the radiation received. So here we have our refracting telescope. This is very similar to what Galileo used. Galileo did use a refracting telescope, although its lens and its eyepiece were much closer in size, so it didn't have as much resolving power. But in general, a refracting telescope is designed to collect light in the visible part of the spectrum, and it uses lenses to collimate and focus the light to a distinct focal point. The resolution of this image at the focal point depends upon the separation between the lenses as well as the quality of the lenses, and this is where you can observe it with your own eyes through an eyepiece at the fixed end of a telescope. The resolution is dependent on two aspects of the design: the aperture, which is the opening size of the diameter of the telescope, that front end where the lens is. So the larger it is, this allows more light and more intense light to come in, and the smaller would mean less light and less intense light. And then at the end of a refracting telescope is at the end of the refracting telescope, and also dependent for the resolution power, is the magnifying eyepiece. This adds additional focus and can be used to clarify images and magnify them based on their distance, and also the lens properties in itself. The lens in the eyepiece, that is. Another type of telescope is the reflecting telescope, which is different than the refracting telescope, which we just saw. Actually, my first telescope was a reflecting telescope, and it's now one of the most common types used in astronomy today. So, due to limitations in refracting telescope design, I would say most notably lens size, because it's hard to make very large, perfectly shaped, curved lenses. Refracting telescopes are pretty often limited by just being expensive. So it's much more efficient to use a reflecting telescope because it's easier to create reflective mirrors that then redirect the light to a focal point. So unlike a refractive telescope, the eyepiece here acts as the optical lens to resolve, focus, and magnify the image at this new point. However, for a reflective telescope, the incoming light redirection allows for various locations of the eyepiece. So you can actually have the eyepiece in different spots along the tube of a reflecting telescope based on the design of the mirror and the secondary mirror, whereas for a refracting telescope, you always have to have the eyepiece at the very end. But similarly, with the refracting telescope requiring more expensive and precise lenses, reflecting telescopes also have a similar problem where the larger you go, the more limited you are by the design. once you get a mirror so large, it starts to warp and it starts to stop being such a perfect mirror and is not able to reflect and focus the light as well. So, despite ideally a bigger telescope being better magnification, intensity, and resolution, this often is a very difficult thing to overcome. Or the design limitations are often very difficult to overcome to get better magnification, intensity, and resolution. Because eventually it just won't be efficient monetarily to try to keep making things that keep failing or will only last for a short time. So, to overcome these limitations, astronomers and engineers have been very clever with their use of technology to improve exposures, which is a term given for the amount of light collected in a given amount of time, and the ability to precisely collect that radiation with a really high degree of sensitivity. This, I mean, you know, from if you ever have used like a digital camera, when you start zooming in on those images, they've got a much greater detail than we can see with our eye when we're zooming in on things far away. So cameras, like digital camera technology, is really, really important for astronomy. By using these digitizing devices, we can collect light that is much lower intensity and create images that are taken over a longer period of time than just what we can see with our eyes. So like our eyes are only able to see things on I I don't know, I think like a 1/125th of a second. Our reaction time is pretty slow compared to how long a camera can leave its exposing instrument open. My camera from my telescope can record for up to 30 seconds. And I know that when I look at something with my eyes, I'm only getting these individual snapshots one after another. I can't leave my eyes open for 30 seconds and see something as more intense than before. So, using these techniques, astronomers have also created mappings of other radiations, of the other radiation at other wavelengths based on scaling intensities. And so we can help resolve images for spectra for things we can't see without our eyes as well. So let's look at some other spectra because we've been talking about the spectra recorded in the visible, but there's other wavelengths which we've talked about. So for the infrared, this is the form of heat radiation that is outside the visible light spectrum. So to visualize the intensities of this infrared radiation, digital devices measure the number of incoming photons at different wavelengths, and then it's these intensities are mapped to the visible part of the spectrum to produce an image so that we can interpret how much infrared radiation is being emitted at a given location. So we can see from this image on the right, we've got this man with his hand inside the garbage bag, and you can't see his hands with visible light. But when we look at him with infrared light, we can see his hands through the garbage bag. However, when we think about his exposed skin, we can see that in the infrared, his skin is glowing much more intensely than the hands in the bag. So using this mapping, we can understand a bit more about what we're seeing. So there are some limitations though for the infrared because heat is everywhere and surrounding the detectors. So astronomers have to find ways to overcome background heat when they're looking at infrared sources. One way to do this is to develop infrared detectors that produce very little heat of their own, and also to put those detectors in isolated sub-freezing environments. So ground-based infrared telescopes often are, I believe there's one in the South Pole, but another way is to put them in space. So the James Webb Telescope, which launched in 2021, Christmas Day, is an infrared telescope. And rather than deal with all of the background heat here on Earth, they said, let's just put the infrared telescope in space. It'll be happier there. There's also radio wave astronomy. Radio waves are everywhere, not just talk radio and music and sports, I guess, or XM radio, but there's also countless astronomical sources emitting radio waves. So, radio telescopes have similar limitations to optical telescopes in that you want them to become larger and larger so that you can absorb fainter sources and things that are farther away. So, we can see on the right, we can see a picture of a radio telescope out in Green Bank, West Virginia. I've actually gone out there myself, and those things are huge. That image really doesn't do it justice, and it's really crazy to watch these things rotate. These radio telescopes are fully rotatable, and they move at relatively fast speeds for something that large. It was really impressive to see, and I would highly recommend if you guys are ever out in West Virginia to go check it out. It's a really cool place to learn about radio astronomy, other than this course, of course. So, another obstacle for radio astronomy is the background. I was just talking about how here on Earth we've got all of these background sources, all of this talk radio and political radio and XM radio, all of these things are not interesting to astronomers and actually serve as background noise. So Green Bank out in West Virginia is actually in a radio quiet zone. Federal laws restrict the ability to for radio broadcasters to have their towers out there, and so it is actually very radio quiet out there. And the radio spectrum is also incredibly large. It is much larger than the visible spectrum, which the visible spectrum is just from 400 nanometers to 700 nanometers. The radio spectrum is, well, despite having wavelengths much longer, it's pretty much like everything from like half a meter onwards. Those are all categorized as radio waves. So it's an incredibly large spectrum, and there's a lot of things emitting at different points in this spectrum. So it's very difficult to map these radio wavelengths that we're recording to visible stuff, to this visible stuff, because the visible has a narrower range. We just can't do a one-to-one. And so to overcome this and improve the quality of radio wave observations, interconnection linking between many radio telescopes around the world is known as an interferometer, and this is used to help improve the range of observations, resolutions, and faint signals that we are looking at, which are much fainter relative to high intensity background sources. So if you ever saw that famous picture recently of the black holes that were recorded with radio telescopes, those were recorded using interferometry to connect radio telescopes around the world to give us essentially a radio telescope with a dish the size of the planet itself, which that's really cool. We effectively turned the Earth into one giant radio telescope. And you could expand that by putting radio telescopes out into space and giving us radio telescope dish sizes that are effectively many times the size of the Earth. And that's what future missions are looking to do. So there are some obstacles. We've talked about these background sources as being one of them. But all of these modern ground-based telescopes have other things that they have to overcome. For instance, they have to overcome the weather. The clouds will block out optical light. The wind will make it unsafe to operate telescopes. Rain will absolutely make it unsafe to operate some of the optical telescopes. But the radio telescopes, I think, can work in the rain relatively fine. Um, but these telescopes are often in very remote locations, which try to minimize these weather conditions. Some are on top of mountains, like out in Kitt Peak in Arizona, or on Mauna Kea out in Hawaii, above the clouds even. They've put telescopes here still on ground based, but they're above the clouds. There's also Earth's atmosphere to deal with. Earth's atmosphere is very good at absorbing a lot of electromagnetic waves, especially in the infrared and ultraviolet. So the liquid, the moisture in our atmosphere is very good at absorbing infrared light. So we can't see infrared light from ground-based telescopes nearly as well as we can from space-based telescopes. There's also light pollution. So if you're in the middle of downtown and you look up at the sky, you're probably only going to see a few stars. But if you're out in the country, you're going to see hundreds of stars. And that's just an example of light pollution being one of these background radiation sources. Keeping the lights on at night does make us feel safer, but it also means that we can't see the night sky as well. All of these houses and cities, and especially these empty parking lots at night, when there's no one there and there's no cars there, and they still have their lights on, this is causing light pollution in the sky, and telescopes in bright areas can't detect the faint objects that they're trying to study nearly as well. And so modern telescopes and observatories are often located very far away from high population centers and light sources. But also the air itself is turbulent. And if it's windy, and not just too windy to use the telescope, but even if there's just a little bit of a breeze, this will cause the images to actually distort, and the turbulence themselves will cause blurs in the image. So if you've ever seen a star that's low on the horizon, or a star that is not low on the horizon, just any if you've ever seen a star that is twinkling, this is because the air is turbulent. The light is coming through air that is of different densities and has different moisture contents through it, and it's swirling about and it's blurring the images. A lot of these obstacles can be overcome by making some adjustments, but there are some that are just generally unavoidable, like that turbulence of the air. No matter where you put it, you're still going to have a little bit, and you're still always going to have some background noise as well. And so you need filtering devices to eliminate background noises. But one of the cooler, more recent advancements in ground-based astronomy is to do away with this turbulent air by being able to model that turbulence and account for it in a process known as adaptive optics. Adaptive optics uses computer models to adjust and compensate for that disturbance in the air when we are looking in the optical part of the spectrum. And then we can get the resolution increased based on these adaptive optics. And so that's really useful for ground-based astronomy, particularly because it's much cheaper to put adaptive optics on a telescope than it is to launch a telescope up into space. And we'll also see that these ground-based telescopes, or some satellite telescopes, are often limited by their size. So, like the ground-based ones, they are limited by how large they can get, but if we think about a space-based telescope, that's extremely limited by how large it can get, because we have to then send that into space. So being able to use adaptive optics on telescopes here on the ground is incredibly useful and efficient, and it's just really cool. We mentioned that the atmosphere kind of filters out some of these wavelengths, and so there are a couple ways to get around that. For the infrared, we can actually not only can we put the telescopes out in space, but we can put a telescope up on a plane and fly that higher up in the atmosphere. So the telescope that you see on the plane there is called the Sophia telescope, but I think it was actually recently retired. But still, by being so high up in the atmosphere, it can overcome a lot of the distortion due to the water molecules because there's just less of it when you're that high up. However, there's still some up there, and so you want to have a space-based telescope for the infrared to operate at maximum efficiency. This slide mentions the upcoming James Webb telescope, but spoilers, that launched in 2021, so we are actually enjoying James Webb data already. It is a fantastic time to be interested in astronomy because we have the Hubble, which has been providing images for pretty much all of our lives, but now we have the James Webb, which is the next generation of space-based telescope. It's not a replacement because it's doing a different wavelength, but it is the next generation in the sense of it has so many new technologies and it's just really fascinating. And we will learn more about the James Webb on the next slide. So, the James Webb is one of the newest space based telescopes, and it is probably the most impressive telescope humanity has ever launched. So, it launched on Christmas Day 2021, and it now orbits the Earth about 1 million miles away, or 1.5 million kilometers from the Earth, in a point known as a Lagrange point. It is at a specific Lagrange point known as L2, and these are just points in the Earth-Sun gravitational system where the pole during the orbit is about the same. So James Webb can sit at this Lagrange point while using very little fuel. And it's out there because not only does it not have to deal with the atmosphere of space, but it is far away and can position its sun shield in such a way that its instrument is in the shade and very cold. Its instrument package operates at, I think, about minus 390 degrees Fahrenheit. So that is extremely cold and much colder than we could have it operate here on Earth. So not only does it not have to deal with the water, but it can also operate at a much better temperature for observing infrared radiation. There's also some upcoming ground-based telescopes, which include the Large Synoptic Survey Telescope, which will quickly scan the sky every night looking for rapidly changing phenomenon. There's also the Cherenkov Telescope Array, which will look for indirect measurements of gamma rays when they hit the atmosphere. Uh, Studying gamma rays is actually pretty complex just because of the wavelengths being so small. You actually can't really focus them well into a telescope. But gamma rays, when they hit our atmosphere, release a lot of energy. And so we kind of look for the glow after the gamma rays impact, and then we work backwards to determine what the properties of that gamma ray was, what direction it came from, and likely sources based on the glow from when it hits our atmosphere. And then there's also the European Extremely Large Telescope, which might win an award for least creative name, but it will also win awards for being able to collect more light than any other telescope in its size class here on Earth combined. It is going to be the largest telescope in terms of optics, in terms of the optical spectrum, and it will allow us to see extremely far and extremely deep into the sky. I believe that one is being built in the Atacama Desert out in Chile. And that concludes lecture 4. I hope you all have learned a lot and are really starting to get an understanding of how the science of astronomy is so related to this idea of how do we know what we're observing and how do we record it, and how that's linked to the scientific method in itself. It's really a fascinating field, and I hope you guys are starting to really come to appreciate it as much as I do.